Welcome, everybody. This is IAU G2 online conference series. This is about massive stars. And today, after the Christmas break, we have already the eighth seminar. This time is Erin Higgins. And she will be talking about very massive stars, a very exciting topic. And I'm going to introduce her a bit. She did her PhD on massive stars in low metallicity environments at the Armagh Observatory and the Planetarium. And this was in conjunction with the Dublin Institute for Advanced Studies as part of the Lindsay cross-border collaboration. And then after defending the PhD in 2020, she was telling me that was probably one of the first who had to give or to defend the thesis online due to the pandemic. Then she worked as a postdoc research associate together with Jory Bing and Andrea Sander on evolution of world-wide stars as black hole progenitors, and now is still there in Armagh, but now is a postdoctoral researcher, and she's working as part of the Bridge UK network. And the idea is to connect galactic chemical evolution with nuclear astrophysics and stellar physics. So probably she will be telling us a bit about this in the context of her talk. So whenever you want, Erin, it's a real pleasure to give the floor to you.
Thanks, Sergio. So hi, everyone. As Sergio said, I'm Erin Higgins, a postdoc working at the Armagh Observatory. And today I'm going to tell you about stellar wind yields from very massive stars. And so this work's been done in collaboration with Jorik Bing, Raphael Hershey, Alison Laird, Andrea Sander, and Gautam Sabahid as part of the Bridge C UK network. So I'll start by giving a brief overview of very massive star evolution before looking at the recent optically thick stellar ones, which we can now apply in stellar models, before showing you some of the results of very massive stars in low metallicity environments, and finally looking at our recent results of very massive star wind yields at solar metallicity. So if we want to model the lives of stars and learn about the physics that drives their evolution, we need to start with a basic stellar evolution code. Now, there are many options, and by no means this list is not extensive, but currently the widely used public access code MESA is used to test various aspects of stellar evolution due to its adaptable nature. But there's also the comparable GENIC, Stern, Padua, and Franek codes, to name a few. And the main ingredients for any one-dimensional model includes the relevant microphysics, such as the equation of state, opacity tables, and nuclear reaction networks, solving the stellar structure equations iteratively with a reasonable temporal and spatial resolution, and then applying the important macrophysics, such as the treatment of convection and radiation, with prescriptions for stellar winds and angular momentum transport and instabilities. So this abundance of information is then resulting in stellar models, which can in turn be used for population synthesis models, galactic chemical evolution models, and is particularly important for understanding the progenitors of compact objects and supernovae types. So there's important considerations that we need to make whenever we run stellar evolution models and try and use these to connect our theories with observations. So for example, every stellar evolution code that's one-dimensional will have, of course, free parameters which account for the assumptions that are made when you're trying to treat a 3D process like rotation in a one-dimensional code. But equally important is the implementation of the various stellar wind prescriptions which are available, and particularly when you apply the correct mass loss rate and metallicity scaling at each evolutionary stage. And so you can see that by looking at this HR diagram on the right-hand side, that by applying different assumptions for internal mixing or mass loss rates, that the variation then that this would lead to and where you would turn from a red supergiant to a Wolf-Rayet A star can be quite dramatic. So you can see that this is the end of the main sequence and shown here in the yellow lines, and this is shown for two different core overshoot parameters, 0.1 or 0.5. So you can really change the evolution depending on the assumptions that you make. So we know that, say, for a 20 or 30 solar mass star, that you could evolve from a protostar towards being a blue supergiant, eventually expanding as a red supergiant before collapsing, expanding as supernovae and leaving behind either a neutron star or a black hole. But in this talk, I'm going to focus on very massive stars, and that's because the most massive stars, they can dominate the chemical enrichment, mechanical and radiative feedback, and the energy budget of their host environments, including young clusters. And in fact, a top-heavy initial mass function, or IMF, was found in the 30 Doradus region of the Tarantula Nebula in the Large Magellanic Cloud. And that suggests that not only do these very massive stars dominate the light from such clusters, but also they're dominating the mass. And we've also observed very massive stars in the Arches cluster of the Milky Way, with current day masses of up to about 100 solar masses. So we find that there are four key traits of very massive star evolution. So they evolved chemically homogeneously or fully mixed. They have been observed in a very narrow effective temperature range, and they exist and live their lives very close to the Eddington limit. And so as a result of this, they experience very strong stellar winds. So here we can see that with increase in mass, the core to total mass ratio increases. And that means that above about 200 solar masses, the star is almost fully convective. And since the entire star then is convectively mixed, these very massive stars evolve almost chemically homogeneously. And so you can see from this Kippenhahn plot or a structure diagram of a 400 solar mass star that the convective core is almost the entire total mass, with just a very small envelope on top. And as it strips here with mass, you can see the effect of stellar winds as well. But this effect of chemical homogeneous evolution becomes very important through our study. And it also means that the evolution of these very massive stars is insensitive to things like the convective core overshoot parameter and rotation rates. And this is something that we've also tested. But here we have the observed WNH stars, which is the spectroscopic classification of very massive stars, if you like. They are nitrogen-rich, hydrogen-rich, Wolf-Rayet type stars that are observed spectroscopically. But these very massive stars have been shown along some transition and O stars for the Arches cluster 30 Doradus region, NGC 3603 and R136. So you can see the four black dots with the error bars are for NGC 3603 and the R136 clusters, and the blue triangles are showing then the WNH stars from the Arches cluster in the 30 Doradus region. And you can really see the narrow range of observed effective temperatures that these very massive stars are observed on, but within about 0.1 dex. Another key feature of very massive star evolution is their proximity to the Eddington limit, which basically defines the condition of outward radiative acceleration balancing the inward pointing gravitational acceleration. So at higher and higher masses, the proximity to the Eddington limit increases as the luminosity to mass ratio increases. And so in order to account for this, stars may inflate to very large radii with low density envelopes. And this can cause a density inversion, as we can see from this plot from Grafner 2012, where the outer radius has a small increase in the density of the outer layers. And finally, as we can see, both theoretically predicted and empirical results have shown that there's an enhanced mass loss rate that's experienced by very massive stars. So in 2011, Yorick Vink performed Monte Carlo calculations for stars with masses up to 300 solar masses. And he found a kink or an upturn in the mass loss rates for the highest masses considered in their grid. And below the kink in the optically thin O star regime, they actually found that their hydrodynamically consistent results agreed very well with those from the Vink 2001 prescription. And so above the kink, they found a very steep dependence of the mass loss on gamma E, or the luminosity to mass ratio. And so in 2011, Yorick found this increased dependency of gamma or luminosity to mass of an increase from 2.2 to 4.77. And this actually remains in agreement with the empirical results that are shown here by Bessemer. So in 2022, a PhD student in our group, Gautam Sabahid, developed a new mass loss implementation for very massive stars, where below the transition points, models would implement the Vink 2001 wind dependencies that are shown here, while above the transition mass loss or above the transition point, the new dependencies of luminosity and mass would be adopted from the relations of Vink 2011. And so the base rates then are calibrated at the transition point, and this transition point is calibrated for absolute rates from observed transition stars and are anchored where the Vink 2001 agrees with Vink 2011 rates. So here we can see the results of implementing this new wind prescription for a 100, 200 and 400 solar mass star. So we compare on the top panels, if you were to apply the Vink 2001 relations to very massive stars, and compare that with the updated increase or enhanced ones with this luminosity to mass scaling. And so you can see that the higher, the upper plots here evolve horizontally and they actually inflate, rather than the bottom plots here, which evolve vertically due to the increased mass loss. And so they don't inflate, but rather decrease in luminosity and evolve vertically, as you can see in both of these diagrams for different metallicities here. And so this updated very massive star wind implementation now provides models which lie in good agreement with the observed very massive stars in both of these clusters in both metallicities. And so in fact, this luminosity to mass relation provides higher mass loss rates to the effect that a steep drop in luminosity decreases the inflation and decreases the mass loss rate due to having lower luminosities and masses. And this creates like a self-regulatory effect, which leaves very massive stars evolving at constant temperatures, as you can see here. And so we found this self-regulatory behavior to lead to quite an interesting result as well, that regardless of initial mass, stars can evolve to about 50 solar masses after around 1.6 million years. And beyond this point, it becomes very difficult to determine the initial mass, which can be anywhere from 100 to 1,000 solar masses. And so the details are also found in this paper that we published in 2022. And in here, we also talk about how we use the surface hydrogen abundance, which can be used as a decipher to break the degeneracy in what the initial mass range could be. So now we have a new mass loss relation, which is implemented in MESA through a new subroutine, which applies the optically thin O-star relation below the transition point and enhanced optically thick mass loss relations for above the transition point. But one additional major factor in the evolution of very massive stars is, of course, the metallicity of its host environment. So as massive stars recycle fusion material over generations and generations, they're enriching their host environments over time and lead us to the now metal-rich universe that we experience, which would be very, very different from the early universe, which would be quite metal-poor. And these differences then lead to changes in the stellar evolution, since the metallicity of stars can affect things such as the stellar winds as they experience, mainly due to the iron content, but also the compactness of the star and therefore the evolutionary path that they'll follow, including the fates that they'll have. So we can see that from this figure from Hager in 2003, that the evolution of a 40 solar mass star at low metallicity would have a very different fate than at high metallicity, either leading to a black hole or a neutron star. So if we consider the evolution of very massive stars at low metallicity, we might find that their evolution towards about mid-oxygen burning starts to become unstable. And that's because stars with a certain CO core mass of around 37 solar masses don't collapse to form black holes at the end of their lives, but they rather rip themselves apart in paired instability supernovae, leaving no remnant behind. And so in the lower mass range of this regime, we can also have pulsational pair instability supernovae. And this occurs where large eruptions from pulsations can lead to the loss of significant amounts of mass before the pair instability happens. And this also leads to something called the pair instability mass gap, which affects the black hole mass range as well. And so this region where the pair instability boundary happens can happen at different mass ranges for different metallicities. And this is directly impacted by the mass loss history of stars during their core hydrogen and helium burning stages. So in September 2019, we detected 2 black holes in a gravitational wave event, which in theory should lie in this pair instability mass gap. And these black holes were a massive 85 and 66 solar masses. And so we wondered from our theory, which should previously have said, you know, there wouldn't be black holes above about 50 solar masses. How could these 85 and 66 solar mass black holes exist while outside the pair instability mass gap? And so some suggested that before the 85 and 66 solar mass black holes, that there were 4 black holes and therefore we were observing the second generation gravitational wave event. But the problem with this is that it probably takes so long for the in-spiral of these black holes and to get so close that to have a second generation black hole collision or gravitational wave event would be quite unlikely in the timescale of the universe. So at Armagh, we set out to evolve stars towards black holes of masses on the order of 85 solar masses without any exotic inputs, and just with the aim of trying to better understand how a single star could avoid the pair instability gap and form such a massive black hole. And so we were able to form an 85 solar mass black hole within a few days by applying a moderate metallicity of about 10% solar and with an initial mass of around 100 solar masses. And so we found that a blue supergiant progenitor, which had quite a high envelope compactness, meant that we wouldn't lose substantial mass through red supergiant winds, but we also wouldn't reach the critical CO core mass that would trigger the parent stability by maintaining a low core mass. So this meant applying a low convective core overshoot parameter in alpha of 0.1 and relatively low rotation of about 20% critical. And in fact, Ethan Winch, a PhD student in our group, is currently working on a large systematic follow-up study. So keep an eye out for this, which will be coming out very, very soon. But if we turn now from the low metallicity environments of very massive stars to the more local metal-rich environment, we find that very massive stars actually play a key role in the chemical enrichment of galaxies. So the nucleosynthesis of stars and then the subsequent ejection of heavy elements through their stellar winds or supernovae is the reason that we have such a metal-rich environment today in our own galaxy. And so in a recent publication, which you can find here, anyone who has their phones or is tech savvy can follow this QR code and find a link to this paper where we looked at the contribution of very massive stars from stellar wind yields. And in this paper, we mainly focused on the hydrogen burning nucleosynthesis cycles. And these are the CNO cycle, the neon sodium cycle, which follows the CNO cycle, and also the magnesium aluminium cycle. And so we focus on a few key isotopes, such as the carbon, nitrogen, oxygen, but also the neon 20, neon 22, sodium 23, and then aluminium. So there's a radioisotope 26 aluminium, which is very important, and also the proton captured aluminium 27. And so within this project, we calculated a grid of stellar models with initial masses scaling from 50 up to 500 solar masses, and they were calculated at solar metallicity from the zero-age main sequence all the way until core oxygen exhaustion. And we compare models which apply the previous VINC 2001 mass loss relation and compare that with the updated models which now apply the enhanced VINC 2011 optically thick mass loss relations. And so we include a large nuclear network of 92 isotopes, which covers all of the relevant reactions until core oxygen exhaustion, and provide chemical wind yields, both for the main sequence and for the post-main sequence evolution. And so you can see here a HR diagram of the evolutionary tracks for 100 to 500 solar mass models. And you can see these are the enhanced mass loss models, which drop dramatically in luminosity at constant effective temperatures. And then this is the core helium and later burning stages. And if you have a look here at the mass evolution with time, you can also see that the dashed dotted lines would apply the VINC 2001 relations compared then with the VINC 2011 relations, which are in the solid tracks. So there's quite a difference here in the mass evolution as well for these models. Now, so there are two ways that we can provide chemical yields. So first, if you're interested in stellar winds, as we are, then we can provide ejected masses in terms of solar masses. And to do this, then we multiply the mass loss rate by the surface abundance of a given isotope at each time step, and then integrate this over the lifetime of the star, or maybe over an evolutionary phase, like the hydrogen burning phase or the helium burning phase or so on. And that can provide then an ejected mass for a given isotope. But on the other hand, if you're interested in galactic chemical evolution, then we can also provide the net wind yields, which are more representative of the change in a given isotope, which is then released back into that host environment. So therefore, at each time step, we take the difference of the surface abundance of a given isotope relative to its initial abundance before multiplying this by the mass loss rate and then integrating this again over the lifetime of the star or an evolutionary phase. So here we can see the main effects of adopting the two various wind relations, either the optically thick enhanced ones that are on the left, and in comparison, applying the optically thin O-star relation on the right to very massive stars. So we're looking at the surface evolution of a 300 solar mass star, where time evolves from right to left, because mass is on the x-axis here, and this is the surface abundance and mass fraction on the y-axis. So as the star loses mass with time, and we strip these outer layers, time is then evolving from right to left. And then this grey shaded region is the mass that's left at the end of the core hydrogen burning stage. And so the key difference between these two models are that you can see 100 solar mass difference in the mass that's remaining at the end of the hydrogen burning stage. And that means that there is 100 solar masses difference in the amount of yields that this star would provide back into its host environment. And that means that the updated enhanced VINC 2011 models, they're providing 10 times more hydrogen processed elements, such as nitrogen or neon, sodium, and aluminium-26, when compared then with the O-star relation applied to very massive stars. And here we have a more detailed version of this plot where we show more isotopes as they evolve at the surface with time, again from right to left. So we can see here that nitrogen enriches very quickly at the start of the CNO cycle at the expense of carbon and oxygen. Also, we can see that this neon 20 line remains constant, and that's because the neon sodium cycle is regenerative of the neon 20. While the neon 22 decreases and the sodium 23 increases. And so at the start of core helium burning, as you can see in this hydrogen exhausted core here, the neon 22 increases dramatically at the expense of nitrogen 14. And finally, we can see that the aluminium 26 increases dramatically at the start of core hydrogen burning and then remains increased throughout the main sequence. And so everything that's in this white region here can be attributed to then the yields through the winds that you would experience for a star of this mass. And everything that's left in the grey shaded region would then be representative of the supernova yields. So throughout the paper, we provide tables of ejected masses and net yields for both sets of models and adopting either the VINC 2001 or the VINC 2011 enhanced ones. And we can see here for our model that applies the VINC 2011 one prescription, that they're ejecting twice as much hydrogen, helium, nitrogen, neon, sodium, and silicon, and up to 10 times more of this radioisotope 26 aluminium. And a key point that we find throughout the project is that where the star loses mass, or at a given point where the star is losing mass and where the mass loss rate is highest, has a big effect then on the amount of a given isotope that would be ejected. So for example, if you lose lots and lots of mass during the core hydrogen burning stage and there's less helium left by the time you get to core helium burning, then you will eject less carbon and helium processed isotopes as compared to then hydrogen processed elements. And so, as I mentioned at the start, we provide yields for the entire evolution, including the post-main sequence, but mainly for applying the enhanced appropriate wind rates now for very massive stars. And what we found actually was that 95% of the total wind yields are produced already on the main sequence, compared to just 5% of the total wind yields which are ejected on the post-main sequence. And we also find that single stars with initial masses below about 50 solar masses don't eject any meaningful 26 aluminium, but very massive stars are ejecting orders of 10 to the minus 2, 10 to the minus 3. And so that means that they could be a large contributor of this radioisotope into our own galaxy. So we also found that a 100 solar mass star is ejecting 100 times more carbon, neon, and silicon than a 50 solar mass star. And so we started to look then at what the effects would be on the IMF. And we found that the IMF weighted yields, which are also provided in the paper, showed that around the transition point of about 80 to 100 solar masses, these stars were ejecting more and more carbon and oxygen than the higher mass stars. And that's because they are not fully mixed, they're not chemically homogeneous, and they don't then lose a significant amount of helium before it's been processed on the post-main sequence. But during the entire evolution, we did find that these IMF weighted yields showed that very massive stars were yielding 10 times more, even still 10 times more processed elements than, say, a 50 solar mass star. So they yield positive amounts of helium, nitrogen, carbon, and neon-22 relative to their initial abundances when compared with O-type stars that are about 50 solar masses. So they have quite a dominant role to play. And finally, we noticed that the vast amount of 26 aluminium that's been ejected by these very massive stars was even still a factor of 10 higher than canonical stars whenever we weight these by an IMF. And that means that the 26 aluminium, which we've observed in the galactic plane and has been suggested to be a key ingredient for the early formation of the Earth might be attributed to very massive stars, which have also been seen in the galactic plane. So now if we have a quick look at the consequences of this enhanced mass loss prescription on the post-main sequence, we actually found that regardless of initial mass, these stars are completing their hydrogen burn phase with masses of around 32 solar masses. So you can see this, this plot is also in the paper and started with an initial mass of 300 solar masses, but the plot looks exactly the same for a star that started its life with an initial mass of 200 and so on solar masses. And so you can see here that this is now the helium zero-age main sequence, again, evolving from right to left until you reach the helium terminal age main sequence, or the helium exhausted core, which is enclosed in the grey shaded region here. And the reason that we now look at these stripped helium stars is that they also experience strong metallicity dependent ones. And so they might also be an important source of chemical enrichment back into their environments. So before 2005, it was considered that the winds of Wolf-Rayet stars could be driven by carbon, but as helium-burning objects, they self-enrich with carbon throughout their evolution, and this means that they would experience the same strong winds regardless of metallicity, regardless of their host environment. But in 2005, Jorg Vink and Alex de Coter found that it was indeed the iron lines that were driving the winds of these Wolf-Rayet stars as well. And this was a really important finding for forming black holes, which were heavier than about 30 solar masses. So you can see that the carbon enrichment here would lead to the maximum black hole, regardless of metallicity, of about 20 to 30 solar masses. And in comparison to that, if you apply the iron scaling, metallicity scaling, to Wolf-Rayet winds, you can now create larger and larger black hole masses. So this was also really important for forming black holes and a key finding for the first gravitational wave detection, which were found to be 30 to 50 solar masses. So this was a really important study. And now a recent development by Sander and Vink in 2020 has provided us with these nice hydrodynamically consistent stellar atmospheres for Wolf-Rayet winds. And so we've applied this new mass loss prescription from Sander and Vink in our upcoming work on Wolf-Rayet stars. So we've calculated a similar grid of stellar models with pure helium stars, and they've got initial masses on the helium ZAMs from 8 up to 50 solar masses at solar metallicity again. And we apply again the large nuclear network of 92 isotopes, which includes all of the necessary reactions until core oxygen exhaustion, and provide chemical yields for the various Wolf-Rayet phases. And so we can see here a comparable model from our very massive star paper, where the helium ZAM starts here for a 32 solar mass model. And as the surface strips of this nitrogen quite quickly, it then enriches in carbon and oxygen as the helium processed isotope. So this is the helium, which drops dramatically here as it enriches with carbon and oxygen. And so the neon 22 that you can see, this orange dashed line here, increases dramatically at the expense of nitrogen. And that's because nitrogen double alpha captures to give you neon 22. And that's produced almost instantaneously. And it's the most abundant neon isotope that would be observed while observed as a carbon-rich Wolf-Rayet star. And so we find that these Wolf-Rayet stars are ejecting a factor of 10 more carbon and neon 22 than main sequence stars. And finally, we have found that the consequences for observable Wolf-Rayet subtypes, as I mentioned, the observable surface enrichment and therefore Wolf-Rayet subtypes can be dominated where stars lose mass. And so if stars are losing significant amounts of nitrogen-rich material during the main sequence, then the Wolf-Rayet star will appear very quickly as a WC star and much earlier in the post-main sequence evolution. So here you can see that when the nitrogen-rich layer is shown here, that it would be observed as a WM star, and the most dominant neon isotope that would be detected would be neon 20. In comparison, whenever the star strips of nitrogen and enriches in carbon, the most abundant neon isotope is neon 22. And this is when the star would present as a WC star for the majority of the helium burning lifetime. So with that, I am already going to leave you with my conclusions, if I can get them back here, which are that 95% of the chemical wind yields that we find from very massive stars are already lost on the main sequence, with only 5% lost during the post-main sequence. And so the majority of the yields will be hydrogen processed elements such as 26 aluminium, nitrogen, and helium. And even when weighted by an IMF, these 100 solar mass stars are still ejecting 10 times more nucleosynthesized elements than a 50 solar mass star. We've applied this new Sabahid 2023 enhanced mass loss relation for very massive stars, and this can change the yields by up to 100 solar masses from stellar winds. Isotopes such as the neon-22 and magnesium-24 might be key tracers for Wolf-Rayet evolution and tracing the chemical enrichment of galaxies. And this detailed nucleosynthesis is providing deeper insights into the progression of Wolf-Rayet subtypes and their origins. So with that, I will already thank you for your attention and take any questions.
Okay, thank you very much, Erin, for this very nice, interesting talk and interesting results. So now time for questions. I have one question myself. So all these are prediction by the models, but could you comment how this can be tested or constrained with observation? How is the usual way people is doing that? Because I imagine that with maybe galactic chemical evolution models or more direct observation, what are the clues we have observationally?
Yeah, so there are different ways that we can test these. So with Wolf-Rayet stars, we can test, of course, the surface abundances, so the CNO abundances and as well as neon. And this is something that we're looking at now with this upcoming work. But of course, you can also use these wind yields and apply them in galactic chemical evolution models. But of course, this usually relies on taking wind yields from different sources and then putting this into a larger model. So this might tell us a bit less. But we're also looking at some tracers such as fluorine and things like this, which are and different ratios like the neon-22 to neon-20 ratio in the galaxy. And the carbon-12 to carbon-13 ratio in the galaxy. So these are observations which we can compare also our model data to.
Okay, so if anyone has any other question, please raise your hand in the question here. It cannot be. So even for the students or anyone who wants to, even if you think it's a naive or easy question, go ahead. It's a very good opportunity. You have an expert here. So Alex, please go ahead.
Okay, congratulations, Sari. Very nice talk. Just a short question because I got lost in one part. I mean, when you show the numbers about the ejection of different elements, what is the unit of measure of that numbers? Because I mean, I saw you put 10, you put 20 something. Yeah, those ones are a mass fraction or a mass or.
Yeah, Alex, so these are, thanks for this question. These are all provided in solar mass units. Okay, so these are ejected masses on top and the net yields on the bottom. So these are relative to the initial composition of the host galaxy, and these are in solar mass units. But the abundances that we show in figures like this are in mass fractions.
Okay, perfect. Thank you so much.
Any other question here? Someone from the library? So maybe, yeah, go ahead and tell us who you are.
Hello, it's Laura, and thanks for the talk, Erin. I was just wondering, you were mentioning aluminium-26 as being an important isotope to measure. Is that your most constraining isotope for using the enhanced mass loss rates versus the old ones? Or are there perhaps other ones as well which are equally as important or almost as important?
Yeah, this is a great question, Laura. So, I mean, there are lots of isotopes that we want to address. I mean, the key ones are probably observable are the nitrogen ejected masses, carbon, oxygen, neon, and things like that I focused on. The reason that we're so excited about the 26 aluminium, this radioactive isotope, is because there's 3 solar masses of this isotope observed in the galaxy, and we don't know what the source was. And for decades, we have been trying to come up with what the key source of this isotope was. So we know that massive stars are the main culprit because you need a very high central temperature, above about a log of 8. Okay, so 10 to the 8. So did trigger this magnesium aluminium cycle. So lots of different sources have been proposed to produce lots of 26 aluminium. So Wolf-Rayet stars, rapidly rotating massive stars, very massive stars, and even supermassive stars. But the point is, we find that already in this Wolf-Rayet stage, if I can show you one of these plots, the 26 aluminium is gone. So it decays on a lifetime of about 0.7 million years. Okay, so after the main sequence, the 26 aluminium is mostly decayed and is no longer present. So we're finding that Wolf-Rayet stars are probably not the main source of 26 aluminium in the galaxy. And it may be more likely that these very massive stars, which are ejecting, you know, even though they're rare, they're still ejecting an order of magnitude more than O stars. So yeah, it could be really important for our understanding of the formation of the Earth, because it's expected that this was the heating source that maintained the right amount of water for our solar system. So we don't have like one of these water worlds that you can see in Interstellar or so on.
Cool, thank you.
Renee, please go ahead.
Hi, Erin. This is Renee Oudmeyer. For some reason, I can't get my last name on the screen. But anyway, I was thinking about population 3 stars. Often people look at the abundances in these very old stars to learn about supernova explosions. But would you see traces of your very massive stars and the material that was ejected during the evolution of the star? Would you see traces in those in the abundance of population 3 stars as well?
Yeah, absolutely, Renee. This is something that we're working towards. It's actually the next project after this Wolf-Rayet paper goes out, that we want to look more at the low metallicity population 3 environments, because these very massive stars may still provide significant amounts of each of these isotopes. And so the nitrogen emitting galaxies, you know, this GNZ11 and Sears and so on, these nitrogen emitting galaxies, we're trying to find the source of such a large budget of nitrogen. And very massive stars haven't really been you know, explored enough, I think, in this context. And we think that also the work with Yorick in the past, that very massive stars might still have strong enough ones because of this luminosity to mass relation. So yeah, I think that there will be signatures of these yields in earlier populations, and it's something we want to look at. Again, things like fluorine and neon and so on, these things will be key tracers.
Oh, fantastic, thank you.
Yo.
Hi, Erin. Sorry, I was a bit late when I had connected to you. Maybe you have answered your question before, but anyhow, what would you guess is the, say, realistic error budget of your results, taking into account all our uncertainties in mixing?
Yeah, this is a great question, Joe. So I did mention at the start that the uncertainties that we have at the lower mass end of massive stars, where convective core overshoot and rotation and all of these things are very uncertain, and particularly the implementation of these things in stellar models. But the point about this is the relevant slide. The point is that these very massive stars, they are pretty much chemically homogeneous already, and the convective cores are such a large fraction of the total mass, I mean almost 90% or more of the total mass, that things like internal mixing, whether you use convective core overshoot of 0.1 or 0.5, it becomes irrelevant. And it's something that I've tested in doing these recent papers. We also found that the pressure scale height is becoming negligible as you get out to these higher and higher masses, out to these outer layers. So the fraction of the pressure scale height becomes less and less relevant. And also with rotation, you know, these stars would lose their rotation so quickly that the effects are negligible. But what we did find is the mass loss is really what's dominating the evolution of these stars. And of course, we are anchoring the mass loss rates at the transition point, which is where the mass loss rates are most accurate. But of course, above the transition point, we have an error bar maybe of 30% on that. So the yields are still, you know, an order of magnitude higher than, say, O stars. And while they might be, say, slightly uncertain, we think that the overarching conclusions are still solid.
Okay, thanks a lot.
Thanks, Jim.
Any last question? Library again.
Hi, I don't know if you can see me. Erin, just a quick question and a segue on Renee's comment on very old stars in massive galaxies, you know, giving an indication of what may have happened back then on population 3. I already chatted a bit this with Yorick. I'm very interested in the sodium, because when you look at nearby early type galaxies, one of the strongest absorption line gradients that we have is not magnesium or iron, it's actually sodium. And likewise, one of the stronger absorption line that you see in the stellar medium, when you know, is actually sodium again. So my question is twofold. If I understand a bit your plots, which I don't, I have the feeling that sodium doesn't really change for the models you've shown. And is this because you don't have enough low metallicity? So is this what is coming on? Can you tell us a bit about the sodium, essentially?
Yeah. So the sodium, if you follow this dotted pink line here, you can see that the sodium actually increases by an order of magnitude at the start of core hydrogen burning. So this neon sodium cycle, maybe I can flip between this the cycles as well to show you. But the sodium is actually produced quite significantly throughout the main sequence due to this neon sodium cycle. And so we eject a lot of sodium, and we expect that this is something that would be important for young clusters. So something I didn't mention that I should have whenever Renee asked the question, and thanks for bringing that up, is the anticorrelation. So the sodium-oxygen anticorrelation and the magnesium-aluminium anticorrelations. And so we find that we need to do a little more digging with this, but we have found that we are ejecting so much sodium during the main sequence, and then oxygen in the post-main sequence, that we are actually able to match the trends of these anticorrelations in like globular clusters and things like this. So I think that they will play an important role also in the population 3, you know, early environments. So yeah, sodium, I agree, is a really important isotope.
So is that the case that will increase even more for low metallicity or not?
It's something that we're testing in the next project. There is no reason why the nucleosynthesis would be any different in lower metallicity. So the nucleosynthesis of these particular cycles shouldn't change dramatically. You know, you might generate primary nitrogen and therefore have more neon and things like that to make more sodium. So if anything, we might actually have more sodium in lower metallicity environments. But what we can tell now is that we increase in sodium by an order of magnitude and continue to increase that throughout the main sequence. And at each time step here, you're ejecting that amount of sodium over and over again. So yeah, I think that this will be important for low metallicities, and they probably will continue to produce lots of sodium, but whether or not this is ejected is something that we need to consider in terms of the mass loss rates in these environments.
Okay, so if there are no more questions, thank you very much again, Erin, for accepting our invitation to give this seminar and also sharing your results. And thank you everybody for joining. So I hope to see you in 1 month again with the next seminar. Ciao.
Thanks, Sergio.